Yeah, I think we can more or less slowly start. Yeah, I'm very happy to see many of you here for this year's and first TRR research seminar. And yeah, I'm most happy to welcome Paul Elhorst for this presentation. Paul is joining us from the Netherlands, more specifically from the University of Groningen, where he holds a professorship in spatial econometrics. So in that sense, you will agree with me that he's a very fitting candidate in our joint research center on spatial aspects of energy and transport and the like. Paul, before having served as a professor of spatial econometrics, has held other previous relevant positions, for example, as a professor of regional economics, actually an endowed professorship by the Stichting Leerstoel Regionale Economie in the northern provinces of the Netherlands from 2011 to 2016, and has also been at the University of Groningen before. Actually, his PhD, however, has been, and as well as his master degree in econometrics at the University of Amsterdam. Paul's research in regional spatial economics and econometrics has been very widely recognized. As such, he's been awarded, for example, prizes for best papers in regional science. It also serves the community in various other aspects, for example, as an author of a widely recognized textbook in spatial econometrics, has served in various editorial roles at renowned outlets such as Spatial Economic Analysis, where he's been an editor-in-chief for many years and has held editorial board positions at, one could, let me just briefly summarize sort of all relevant journals in spatial, urban, and regional science, as well as other memberships in associations, published, again, in more or less all the relevant journals in the field. 100 papers in such refereed outlets, has been very active in supervision of thesis, and I could continue here, but won't, because we very much look forward to Paul talking and not me. So yeah, thanks again for coming here. I look forward to a presentation, to an interesting presentation, and the floor is yours.
Okay, thank you, Christoph, and thank you for inviting me here today in Dortmund. Well, I'm talking about this topic. It's based on a PhD thesis of Joanna Chiolas. So if you're interested in the material, please download her dissertation. You can find it using this link. Well, it's one of the chapters in our PhD thesis, and we are updating it or extending it such that we can submit it to an econometric journal. Petros Milionis is also one of the co-authors. So it's dealing with three-dimensional panels, or multi-dimensional panels. And that's a topic that is gaining more and more attention. And if you are interested in this topic, I recommend you to read this book, this textbook edited by Matthias. There are two editions, one in 2017 and one in 2024. They contain lots of chapters on a variety of topics, all dealing with multi-dimensional panels. That's really an econometric textbooks worthwhile to study. But if you read that textbook, the different chapters, you will see that less attention has been paid to the estimation of multi-dimensional spatial panels. So the spatial aspect didn't get the attention that it deserves up to now. So, and that's the topic of my presentation today. And the reason why it doesn't get the attention that it deserves is probably because you face several computational challenges if you work with large data sets. And when you work with multi-dimensional panels, you often have to deal with large data sets. So the estimation of these kind of models, due to the size of the data, is extremely complicated. And you really need to apply very efficient estimation methods, because if you don't, forget about the estimation. It will not work out. We will also I also have an illustration which is based on flow data. And the reason we decided to use flow data is because that's probably the most well-known example of a multi-dimensional. So you will see I will give a couple of examples, all based on flow data, because that's that kind of data is used most often, but there are, of course, also other opportunities or other data sets you can think of. And I focus on fixed effects models, not on random effects, and I will tell you why in a minute. Okay. So if you go into the literature and you look, what kind of three-dimensional spatial panels have already been discussed or have already been analyzed, you will see that indeed there is one part that focuses on computational issues in case of maximum likelihood estimation for large data set, but only focusing on one point in time. So the T dimension is one, so to say, and why we want to estimate these models for panel data. There is another part that analyzes flow data, so specifically flow data, also limited at one point in time. So here there are several studies you can take a look at if you're interested in the analysis of flow data. And one of the exceptions, there's a study of Lesage and Manfred Fischer, Vienna, three-dimensional study, and they adopt a spatial Durbin model. I will tell you what a spatial Durbin model is in a minute. They're based on 5,000 observations. I do not really call that a large data set. According to me, that's relatively small. And but if you look at it and look at the fixed effects that they include in this study, you will see that it is actually a two-dimensional panel data setting. So they sell their paper as a three-dimensional panel data study, but if you look at the type of fixed effects being included, it's actually a two-dimensional panel. And that's a problem that you see in lots of studies. So one of the book chapters in this textbook by Balassi et al. 2024 say that many papers that are sold as three-dimensional panels are actually two-dimensional.
One more question. Can you give an example? What do you have in mind when you talk about flow data?
Flow data, you have trade flows from one economy to another economy, and one country to another country, one region to another region. So you have two cross-sectional dimensions, and you observe these flows over time.
Mm-hmm.
So that is trade data. But you can also think of commuting. You have your place of origin, where you live, your house, your place of destination, and you can observe commuting flows over time.
So in principle, this could be anything.
Yeah, but you can also have sectors.
Gas flowing through a pipeline, for instance.
But you can also say I have data of a particular economy, but it's split it up in different sectors of the economy. So you have sector 1, sector 2, sector 3, agriculture, manufacturing, services within an economy. And then you have also three dimensions over time. There are some studies that look at random effects. So that's also one of the book chapters in 2024 by Legallo and Pirot, two French spatial econometric researchers. But random effects have two disadvantages. The random effects might not be correlated with the regressors in the model. And if you test for this, for example, using the Hausman test, you will find in 95% of the cases, you will find out that random effects need to be rejected in favor of fixed effects. And another reason is, and that's extremely important, if you are a spatial econometric researcher, I'm interested in interaction effects. So I want to analyze whether one flow affects another flow. And if I'm interested in whether one flow affects another flow, I need to sample the whole population. So I'm looking at flow data within the across the NUTS2 regions of the European Union. Yeah, I need to sample all NUTS2 regions, because if I have missing links, if I have white spots on the map, then I'm unable to measure the interactions adequately. So I do not randomly sample a couple of NUTS2 regions from the whole population of NUTS2 regions in the European Union. I take all of them, because otherwise I can't estimate the interaction. And that's why random effects do not fit with the sample design that I'm looking at. So here we come back to the issue from what kind of data. So I start with a three-dimensional panel model, so without spatial interaction effects. So we have dependent variable, and we have regressors with coefficient beta. And here you see these indices I and J. I runs from 1 to n, and J runs from 1 to n. So the economies of origin do not have the same than the economies of destination. But in many cases, they are of course the same. N is equal to M. So the NUTS2 regions, you look at all the flows between the NUTS2 regions. And if we look at trade data, then the dependent variable might be the local value of trade from economy I to economy J. Yeah, so the total cross-sectional dimension is n times m. And so how many NUTS2 regions do we have in the European Union? Oh, 266. So we have so if we have flow data, then we have 266 times 200 times 266, and then you get a huge value of n, more than 70,000. That's what I call a large data set. And then the problems, the computational problems begin the moment that you want to also model spatial dependence. Well, there are a couple of spatial econometric models that are very popular in the literature. So if you are you familiar with spatial econometric models? That's always a very important issue, because otherwise the story will become a bit difficult. But I will give a couple of examples. So the one thing that you can do is you can, that's the model that's used most often, also for illustration, a spatial lag in the regression. So in the dependent variable. So what you more or less assume that the trade flow of between two economies is affected by another trade flow. So you could see that the trade flow from the Netherlands to Germany is affected by another trade flow by Belgium to France, for example, or by the Netherlands to Belgium. And so one trade flow affects another trade flow and vice versa. Because it's vice versa, right? Because one trade flow can affect another, but also the other way around. There's spatial lag in the regression is an endogenous explanatory variable. And you take it up on the right-hand side of the model. So here you have the trade flow of two units, I and J, that's affected by the trade flow of other units. But this regressor then becomes an endogenous regressor, because the trade flow from G to H affects I to J, but also the other way around. So this, we need to take this into account when estimating this model. Another model is that you not only have a spatial lag in the regression, but also in each of the regressors. So it could be that an explanatory variable of the trade flow between the Netherlands and Germany also affects other trade flows. And then you get spatial lags in the regressors as well. We call that a spatial Durbin model. Some people, some researchers say, no, I do not, next to the spatial lag in the regressor, I also want to include a spatial lag in the error term, because there are variables omitted from the model, and they are covered by the error term, but it could be that those variables that are omitted from the model are spatially correlated. Okay, then you get a spatial lag in the error term. And specifically for this literature in three-dimensional literature, you may also get so-called higher order spatial autoregressive models. So instead of one spatial lag in the regression, so the one that I have here, you have three of those terms. Because you can have a spatial lag for the places of origin, spatial lags for the places of destination, or the combination origin and destination. So you can say, oh, well, the Netherlands might be an exporting country. What are the neighbors of the Netherlands that are also exporting to Germany? Oh, you can look from the perspective of Germany. It's importing goods from the Netherlands, but it's also importing goods from other countries, or the combination origin destination. So then you get three spatial lags in the dependent world. So we call it a higher order spatial autoregression. So these are the kind of models that you see most often in the spatial econometric literature in three-dimensional spatial panel data. Okay, so this is the specification, and now you see, now you have this W with an index D. So if we have only one spatial lag, it could be that we are looking at the name, so a W matrix at the neighbors of the export, the neighbors of the importer, or the neighbors of the exporter and the importer. Now, this W, this is always an issue. So the most critical part of spatial econometric is the specification of this W. When are units of observations neighbors of each other? So take Germany. You could say, oh, I look at so in a two-dimensional setting, I look at the countries that share a common border with Germany. And so you say, oh, the Netherlands and Belgium and Luxembourg, etc., France, etc., etc. So then you have contiguous neighbors. But yeah, is that a good idea? An alternative is that you look at the distance. So you take the capitals of Germany and, for example, the Netherlands, or Berlin and Amsterdam, and you calculate the distance. And then you get different measures because the distance between Berlin and Amsterdam is different than the distance between Berlin and Brussels. So then the elements differ. But now you have to translate this kind of thinking into a three-dimensional setting, because now we work with flows. And so you could say, oh, I'm looking at the neighbors of the exporting country, the neighbors of the importing countries, and the combination. But what I do is I start from a pre-specification of this W matrix. The elements that tells whether there are neighbors or not, and what these values of this W matrix are. 1.5 years ago, I was also here in Dortmund at the Statistische Woche, and say, yeah, maybe you can also estimate the elements of the W matrix. And then I showed you how you could do this. That's not what I'm doing in this. So I start from a pre-specified W matrix to estimate the models. A step further would be also to estimate the parameters of this W matrix, but then the computational complications would increase even further. Okay, so what we have is this W matrix, which is then, given the economies of origin, economies of destination, is of n by n. And here the problems, the computational problems start, because this n by n matrix is W. So if I work with that's two regions in the European Union, well, there are 266, so n and m are both 266. Then this matrix, n is, this capital N is the small n times the small m, is 266 squared, so that is 70,756. So my whole matrix W is 70,756 squared. That's more than 5 billion elements. Now, forget about your computer program. That's not gonna work. A matrix that's more than 3,000 by 3,000 already may slows down your computer tremendously. So here is the big issue. How are we going to estimate a model like this if we have such huge W matrix? So up to now, there are hardly any people who have been able to estimate this kind of model for a spatial panel. And we offer a solution. And this is what I show you here is a solution that has already been developed in the literature to deal with this issue. But the question is, can we also apply this in a spatial panel data set? In a cross-sectional setting, it works, but in a spatial panel data setting, it's not so obvious. So that's where the paper is actually about. So if we have this W matrix and we work with this principle, here the neighbors of the exporter, the neighbors of the importer, or of both the exporter and the importer, now we have a full matrix which consists of the exporter matrix, the importer matrix, or the combination with a Kronecker product. So instead of storing, this means that instead of storing this huge n by n matrix, which contains far too many elements, we can also store this matrix, which is 266 by 266, this matrix, same size, or this combination, which are both 266 by 266. That's not a big deal. A matrix storing of 266 by 266 works. We can work with. And we need to use this Kronecker product later on when we calculate the log likelihood. Okay. Let's go back now to the fixed effects, because here I showed you this model, but I didn't talk about the error term yet. So here comes the error term specification. Oh yeah, in a two-dimensional panel, you have 4 options. So you can include cross-sectional fixed effects or not, 2 options. You can include time fixed effects or not, also 2 options. So that means you can include both cross-sectional fixed effect or time fixed effect, one of them or neither of them. So 4 options. In a 3-dimensional panel, you have 2 to the power 6 options. Yeah, that's so much that we only tend to work in this literature with a couple of common formulations that are used most often. And this is information that I took from these studies already available in the text. So you can include pair fixed effects, pair fixed effects plus time fixed effects. But if you look at it, this is actually a one-way fixed effects model. And so you include a dummy for each pair of observations. This is a two-way fixed effects model because you have these pair fixed effects plus one, and a time fixed effects for every time period. So many studies that are sold in the literature as if it's a three-dimensional panel data model, actually is two-dimensional. It becomes interesting, or let's say complicated, the moment that you include origin time fixed effects. So a fixed effect for each economy of origin times the time dummies. So you have these fixed effects for every time period. Also for destination time fixed effect. And finally, you can also include origin time, destination time fixed effects, plus pair fixed effects. But if you look at it very carefully, then you see, oh, wait a moment, this number of fixed effects also increases tremendously when in a three-dimensional setting. So for example, if N and M are both 266 and T is 11, as in our empirical illustration, then in 2D, you already have 76,000, a bit more fixed effects. So that's also an incredible high number. How are you going to do it? Okay. So what we then do is we use the within transformation. So if you're familiar with the panel data literature, the textbook of Badi Baltaki, for example, then it's explained very well how you filter out, how you demean the variables in the model from these fixed effects. So these two, the first two transformations, the standard within transformations, can be found in Baltaki's textbook. But if you have the last equation, 3D, then the equation is much more complicated. So filtering out the fixed effect, it can be done in advance, but the demeaning procedure is a bit complicated. Okay, so we could say, yeah, we do this demeaning procedure and then we estimate the spatial econometric model, one of the models that I showed you on my slide. But the problem in that case is the moment that you add spatial lags into the model and you apply this demeaning procedure, then you end up with bias parameters. This has been shown by Lee and Yu in 2010 in the Journal of Econometrics for a two-dimensional spatial panel data model, but this problem also appears in a three-dimensional spatial panel data model. So we have a kind of a dilemma. We want to use the within transformation to get rid of all those fixed effects. Then we can apply all kinds of efficient estimation methods that have been already developed in the literature. Okay, but at the same time, we want to get rid of any potential biases when we apply these standard within transformation. So that is the puzzle that we need to solve. Okay, the log likelihood function. And so how does it look like for the spatial autoregressive model for one particular type of W matrix? So the exporter matrix, the importer matrix, or the exporter-importer matrix. Well, you get this log likelihood function, which is pretty standard, except for this term, the Jacobian term that you see here. Because we need to take into account the endogeneity of this right-hand side variable, that the trade flow between two economies can affect the trade flow of another two economies and vice versa. Well, this Jacobian term takes into account this endogeneity and avoids that you get bias estimates for rho and all the data. Okay, it has been shown in the literature that this log likelihood function can be solved analytically for beta and sigma squared as a function of rho. You can substitute those analytical solutions into the log likelihood function over here. Then you get the concentrated likelihood function. It depends only on the rho parameter. And then you can maximize this equation, which is only formulated in rho. That's simple. Except that an analytical solution doesn't exist. There is no analytical solution for rho in this equation. So it should be maximized numerically. But it's not difficult because this function is concave and you will always end up with a maximum quite easily. If there are any questions, don't hesitate to ask them. I try to answer them.
I have one question concerning the 3D property that you talked about. So you said that many papers sell their 3D panel setup as so they sell it as a 3D panel setup, but it's actually two-dimensional. So this is maybe 2 slides before where you have the 4 examples. So this that one. So what they do is 1, 2, or 3, and what you do is 4, right?
Now they do 1 or 2.
1 or 2, yeah.
And we do 3 and 4.
Okay.
The difference between 4 is even more difficult than 3.
Yeah.
But these are really 3-dimensional fixed effects.
So the second one is in the end 2-dimensional because you have ij on the one on the u and t on the eta, and then it's 2-dimensional.
That's true. And so if you're for people familiar with the trade literature, I don't know whether there are any researchers in that area. I will see that 2D is the most common specification in the trade literature. So it's worthwhile to have a look at that particular equation.
Then trade literature, not that I'm very familiar with it, they don't do the spatial econometric part that often. So then they will not have the role.
No. But one thing to remember, sometimes the trade literature work with multilateral resistance terms, so that's also a way to deal with interaction effects. But the idea is that we develop a method such that we can estimate these models, but not necessarily trade flow data, but any 3-dimensional spatial panel, and trade flows are just an example. Right, so let me be clear. We only use it as a mean to illustrate how it works. Okay, so now, so here to deal with the endogeneity of this log Jacobian term, we need to, we have this term in the log likelihood function, and now. Here you see an example already developed in the literature by others, how you can still calculate this very complicated term, because I remember these W's are extremely large, more than 70,000 by 70,000. So you can't store these W matrices, but there is a way to get rid of this, to circumvent this problem by calculating the eigenvalues of these smaller matrices of 266 by 266 of the exporter and the importer matrix. So you store these two matrices, you calculate with your computer program the eigenvalues of these two smaller matrices, and with these eigenvalues you can calculate these log Jacobian terms, and well, then you can estimate it. It's as simple as that. Except if the smaller W matrices, of course, also become large. So, and the maximum is about 3,000 to 4,000 units. So if you have a computer program and you calculate this in R or in MATLAB or any other sophisticated computer program, and the smaller W's become greater in size than 3,000 or 4,000 by 4,000, then you can't trust the numerical values of your eigenvalues. Not so much anymore. So you need to be careful with the interpretation. But for smaller matrices, that's not difficult. But remember, if we have, let's say, 3,000 by 3,000, right? So for the smaller matrices, we can deal with 9 million pairs of observations. So I would say that it's already, that for most empirical applications, that would work. There are, of course, researchers who work with zip code data or something like that. So if you divide the whole Germany into zip codes, well, then you might face problems. Okay. But now these biases, and let's look at, there are several biases that could occur. I want to focus on this last equation, to the 2D equation. But there are other biases in other situations as well that might appear. But I'm specifically looking at the three-dimensional spatial panel in 2C and 2D. Okay, so what is the solution? We have these within transformations. They can be denoted by a matrix J. And here, for example, you see the matrix J that eliminates the pair fixed effects in 2A or in 2D, because we have also pair fixed effects in 2D. This matrix, that is in the Baltaki, Badi Baltaki's textbook on panel data. This is the standard. This matrix is all P by T. And to avoid biases, Lee and Yu proposed to work with so-called orthogonal transformations. So I denote them by the capital F. And how do you get these orthogonal matrices? You take the matrix J, you calculate the eigenvectors and the eigenvalues of those matrix J, and then you only select the eigenvectors that have a value of 1. So, for example, this J matrix that eliminates the pair fixed effect has T minus 1 eigenvalues of 1, and 1 eigenvalue that's 0, and we drop the eigenvector of which has an eigenvalue of 0. So we keep the T minus 1 eigenvectors in this matrix F that have an eigenvalue of 1. And then we get a matrix F that is not T by T, as the J matrix, but T times T minus 1. So one column drops off. You transform the data with that F matrix. And then if you do all the estimations, you get rid of the biases in the spatial econometric model. Okay. Now, we have been thinking about, what is the J matrix that eliminates the origin time and destination time fixed effect? Well, we figured out that it is this matrix. It has this particular form, which has n times m minus m plus 1 eigenvalues of 1. So in that case, we get this orthogonal matrix. This orthogonal matrix might again be difficult to determine because it has this order if n is large, of course. So if possible, we would like to calculate this F matrix because it's far too big to determine it mathematically in a computer or numerically in a computer program. Okay. So what we do, we apply the transformation, so the F transformation, and this is how it works. We take we have the y factor of the dependent variable, but we reorganize it in an n by t matrix. So it consists of different columns, And so it looks like this. And then we pre-multiply it by this made orthogonal transformation FNMT to filter out the origin and time the origin time destination time fixed effect. So we pre-multiply it by that. And we post multiply by FT to filter out the pair fixed. Okay, so this transformation filters out also the all the fixed effects. It's an alternative for the within transformation. So the reason why we are doing it is to avoid that we get biased parameter estimates. But now what you see is that due to this transformation, the number of observations go down. So we instead of n times t observations, now we have less observations. So we get a different log likelihood function. Yeah. It looks a bit different because now we have not n times t, but we lose observations. Here you see this Jacobian term, it's not multiplied by t anymore, by t minus 1. And here we have a very ugly W matrix. Oh, here is this matrix again. Here is the W matrix. It's now F, the transpose of F times W times this other orthogonal transformation. So instead of having a W with very nice properties, now we have suddenly an ugly W matrix, matrix with very ugly properties. And due to that, we are unable to apply the transformation, all the efficient estimation methods that have been anymore that have already been developed in the literature. So the F transformations help us to get rid of the biases, but now we have problems because we can't use the efficient algorithms anymore that have already been developed.
And just one question, the problem here is that the W is assumed to have this Kronecker product structure.
Yeah.
Right? And with this multiplication, this breaks down.
Yeah.
That's essentially it. So
Yeah,
you don't maintain this.
Yeah, so and this W is, so it's not capital N by capital N, but it is, it has now this size, N minus 1 times N minus 1 squared. So all these, you lose this Kronecker product. So forget about the efficient estimation method, at least that's how it looks like. So on the one hand, we want to use all the efficient methods that have been developed in the past. But on the other hand, we don't want to end up with biased parameter estimates. So how to do with it? But we have developed a lemma with which that gives us the opportunity to use the original Jacobian term. So this is the new Jacobian term. Okay, it's here again. Here is the original Jacobian term. This W has all the nice properties. There's still this Kronecker product, so we can still estimate this determinant using these efficient estimation methods. And what is the link between the two? Well, we derived analytically that we can get this determinant if we divide this new Jacobian term by 1 minus minus rho. So the parameter of the spatial F divided by this term, as well as divided by this term, which depends again on all the eigenvalues of the smaller W matrices. Now, this expression here, this part already existed in the literature for two-dimensional spatial panels. So that was part of the work of Lee and Yu in 2010. And the second line is the addition that we make to the literature that you can also do something similar in the three-dimensional space panel data. So if you would have 2A or 2B, then this line drops off. And the moment that you switch to 2C and 2D, you need to add this. Here you see the expression for the exporter times importer matrix, but the moment that you have only an exporter or only an importer matrix, then some of these eigenvalues become 1. So instead of these values over here. So this is actually a very important lemma, because that gives us the opportunity to keep using the efficient estimation method, but also to get parameter estimates that are unbiased. Of course, you can, if you want, and this is for a spatial autoregressive model, but if you have a spatial Durbin model, and so you would like to have spatial lags in the regressors, the formula, the lemma doesn't change. When you have a higher order SAR model, you get a different lemma. So that looks like this. And when you have, when you want to extend the SAR model with a spatial lag in the error term, you get 2 instead of 1 Jacobian term. So we can also estimate all the other 3 models. So our purpose is to work this out in detail, to come up with the mathematical proofs, and also to make routines available, such that users interested in this type of research can use those routines to deal with their data sets and their empirical problems. Like I did in the past for 2-dimensional panels back in, I don't know, 20 years ago or something. So, any empirical illustration? Do I have time or? Yeah. Okay. So as I said, we look at NUTS2 regions. So, oh, wait a moment. We have 70,756 regional trade flows. Oh yeah, I said NUTS2 regions, but we also have a couple of countries, because then when you look at trade flows, you also, so we have also the main countries like China and the United States, plus the rest of the world, if I remember well. So something like that. We have a gravity model. We look at different combinations of fixed effects, as well as different combinations of spatial. And what are we looking at? Interpretation of the estimates, goodness of fit, ability to account for spatial dependence, number of parameters that need to be estimated, and not unimportant, the computation time. Okay. So the first one we did is calculate, do we actually have any empirical evidence in favor of spatial dependence or cross-sectional dependence? Well, to find out, you can use the CD test, the cross-sectional dependence test, developed by Passeron, 2015, econometric review. And if you apply his test, so you find there is no cross-sectional, you find no evidence in favor of cross-sectional dependence if this test statistic is between minus 1.96 or plus 1.96. Well, this is pretty outside the confidence interval. So the hypothesis of no cross-sectional dependence needs to be rejected. Bailey et al. Also developed what they call that's in the Journal of Applied Econometrics, very interesting paper about the exponent of alpha that measures the degree of cross-sectional dependence. So 0 is no cross-sectional dependence, 1 is the maximum, and there are different degrees of cross-sectional dependence. And we apply this statistic, we find 0.94, so it's very close to 1. So there is a high degree of cross-sectional dependence in the data. So an issue to take care of. Okay. We started with gravity models without spatial lengths. And so first models that have already been estimated in the literature. So here we have the usual regressors, like the distance between economies, contiguity, common language, things like that. And here, trade agreement, AU membership, common currency, things like that. So that are the typical regressors in the trade literature. This is the model when we include exporter time fixed effects and importer time fixed effects. So that's our equation 2C. This is the model when we also include pair fixed effects. Yeah. What you see here is, oh, at the moment that we include pair fixed effects, we don't get the estimates of a couple of regressors. Yeah, that's because they are perfectly multicollinear. And so we have a pair fixed effect for each two economies. Yeah, then and the distance doesn't change over time. We can't estimate the impact of that regressor. That's what you always see in panel data studies. So a couple of variables that do not change over time drop out. Okay. Well, the R squared and the log likelihood function value. So here, look at the log likelihood function value is minus 900,007, and here it's only minus 3,720. But on the other hand, the number of parameters increases tremendously. And so here we jump from 5,850 to more than 76,000 fixed effects. So the number of fixed effects is far more larger. So the moment that you include pair fixed effect, this number increases tremendously. But if you would do a log likelihood ratio test, so is this a significant improvement? Yes. Despite the tremendous increase of number of parameters. So a likelihood ratio test would tell you that this model is better than this model. And you see that it does have impact on all these regressors. So here you have minus 0.05, here 0.1. So the outcomes really change. You see also the CD and the statistic and the exponent alpha, now not applied on the raw data, but on the residuals of the model. They go down tremendously. And so here we have these high numbers. And here you see that the both drop down tremendously. So that helps to get rid of to cover the cross-sectional dependence. Yeah.
I have a question about the stars. So I assume they are based on asymptotic normality of coefficient estimators, and I wonder, like, to what extent that's a foregone conclusion that this works. So I can imagine that it's not trivial to establish that that the estimator you propose is, well, also follows an asymptotic normal distribution. And well, I'm not saying it doesn't, but I could also imagine that yeah, some conditions are required. So I would conjecture that it's good if you don't have sort of a spatial unit root. So if rho is not one, there's some.
Well, yeah, we didn't include the rho yet. That's on the next slide. So that comes here.
Okay.
So yeah, one thing, of course, is when we calculate these statistics and determine the significance levels, then the issue is, of course, is it robust for heteroscedasticity and all these kind of things. Let me think. I don't think that we included that yet, because including that depends on how you include heteroscedasticity, because you have different options, right? Or you can, of course, heteroscedastic, robust, standard errors or t values and significance levels. Probably they would go down, and then the significance level would go down. So then maybe our 3 stars would be sometimes become 2 stars. Yeah, that's an issue that we are looking. But we can't do all things at the same time. But does that answer the question, or do you want us to do more?
No, I mean, that's well taken about the row on this slide, but like on the next slide, if you have heteroscedasticity or asymptotic variance may be affected, but my question is like before, is it even guaranteed that the estimators follow an asymptotic normal distribution in such a complicated spatial model?
Oh, yeah, no, that, oh, for sure, that is, yeah, of course, then there are a couple of assumptions that need to be satisfied, especially with respect to this W. Right, so the W that specifies the elements of the spatial weight matrix with which we measure whether units are neighbors or not. There are properties that need to be satisfied, otherwise it's the estimator is not asymptotic normal. What's important is that n and n needs to go to infinity. Well, that's okay.
And about the row, can row be anything, or
no.
My question would have been it also has to be.
I'll come back to that question in a minute. Okay. Yeah, one thing for sure is that this and both estimated, you know, it can be, this is the computation, can be estimated in a split second. Yeah. Okay, now your story. What about the row? So here we have a SAR model, estimated by maximum likelihood. So with exported time fixed effect, imported time fixed effect, pair fixed effect. So we now have this model. And we included one type of spatial lag in the model. So we could take the exporter, the importer, or exporter importer. We chose in this column for illustration purposes the import. And why? Because then the R squared is the highest of all three options. Okay. This row, it needs to be in, let's say in the interval, if the W is row normalized, that's what we typically do. So you could say, let's say I use binary contiguity. So I have an importer matrix and I take every region in the sample and I look up what are the neighboring regions of every region in the sample. On average, it's about 6. And so take a particular region in Germany and you look at the neighbors, sometimes it's 5, sometimes it's 8, but on average you have 6 neighbors. So then there are, in every row, there are 6 elements that are 1, and all the other elements are 0. Then you row normalize the matrix, so every element becomes 1/6. So if you have 5 neighbors, every element becomes 1/5. If you have 3 neighbors, 1/3, etc. So every row sum is equal to 1. If you have used that normalization, then this row parameter takes values on the interval -1, +1. Now it's obvious that it is within the interval, so there is no. So if it would be outside the interval, then the model becomes non-station.
Right.
This is the reason why I like maximum likelihood a bit more than generalized method of moments, because the maximum likelihood estimation takes care of the Jacobian term, which guarantees that this row parameter is within the interval. If you use GMM with instrumental variables, you may end up with values outside this interval. There are examples of studies where this row parameter takes values outside this interval. That's generally the case when you look at something that is increasing all the time. So if you have a look at a particular, so let's say the adoption of new technologies, if you try to analyze that over a particular time period, and every year more and more people start using that technology, and so there is an upward trend, then you might get a row parameter that's greater than. So that's something you always need to take care of. What you see here is that when I include one additional parameter, so it's only one additional parameter compared to this one. Here we have 76,069. Here we have one more. But if you look at the CD statistic and the exponent alpha, they also both go down. Here we had 123, 65. Here we have, here both are lower. So this parameter really helps to model more cross-sectional dependence in the data than we already did. So the fixed effects help, but the spatial F also help. You see also that this model already takes much more time to estimate. Here we have the same model. Here we have the spatial Durbin model. So we also include, but not, unfortunately, we don't report them because they don't fit on the screen. Now we also take spatial lags of these three regressors. So we have 3 parameters more. And here we have the higher order SAR, the higher order spatial Durbin model. So we have 3 lags in the dependent variable, and we have also lags in these regressors for every W mate. So the number of parameters increases even more, but you also see that the CD statistic and then the exponent alpha, go down much and much more. So we are better and better able to cover the cross-sectional dependence, the spatial dependence that we observe in the data. It's still not in the interval here, minus 1.96 plus 1.96, but it's getting closer and closer. You see that this model, estimating this model takes 3,782 seconds. That's more than an hour. But if you would try to do this with standard software, forget about it. That's not good. So what we have achieved that we can estimate these advanced models with our efficient software and getting parameter estimates that are unbiased. Oh, here you need to look at the sum of those 3 coefficients. They are, because this is together 1.2 minus 0.33, so it's below 1 again, so the model is stable. So what are our findings? So in summary, regional trade flows are characterized by a large degree of spatial dependence. That it follows from the CD statistic and exponent alpha, but fixed effects help to reduce them to cover this spatial dependence as well as spatial lags. Well, we find significant spatial interactions, so it's worthwhile to take them up in the model. And what's also important is that the impact of the variables, so if you look at the coefficients of the variables, that they really change. So if you use your study to draw policy conclusions on the coefficient estimates, they really change when you take all these fixed effects and spatial lags into account. We are also able to estimate several models with different sets of fixed effects. So we have these equations 2a, 2b, 2c, 2d. We can deal with different spatial econometric models, spatial autoregression models, spatial Durbin model, etc., etc. We can work with large panels. Everything is based on our lemma that links the standard within transformation with this orthogonal transformation. I showed you the computational challenges that we by calculating the log Jacobian term, but similar issues apply to the variance covariance matrix, but then I would need another hour to explain everything. And we can estimate this model in a reasonable computation time. We also, so with these 266, that's 2 regions, we can't show the time benefit, but we can do it for a smaller data set. So if we would work with not 1 regions only, but then with a smaller data set, then we can calculate we can estimate the parameter estimate with our efficient estimation method, as well as the the old ones, and then we can show how much faster it moves. And that's the presentation.